Second reaction, aromatic substitution reactions, is sulfonation. And in sulfonation, we use either sulfur trioxide or sulfuric acid, okay, as our reactants. So without further ado, let's look at the reaction. The full reaction, which is the first step of every reaction, we have to show the full reaction of the procedure or before the mechanism. We have to depict the full reaction so that we know the products to be formed. So we have our raw material, which is the benzene ring, which is going to be sulfonated, and in this case we use 2 molecules of sulfuric acid. So one molecule will pose as a reactant and another molecule will pose as the catalyst. So this one will pose as the catalyst, this one will pose as the reactant, this one as the reactant, and our resultant product has to be our benzene ring okay. Our resultant product has to be our benzene ring with the sulfonic acid attachment. So this is bromosulfonic acid. Yes, yeah, this is our product, which we'll have to realize after sulfonating the plain benzene ring. And as a byproduct, we form water as well, H2O. Accompanied with that, we restore our catalyst, H2SO4. Okay, so as a first step, we show this complete reaction always. So let's look at the step-by-step mechanism of this reaction. Okay, so step 1 is electrophile generation. So we have to generate an electrophile. So in generation of an electrophile, we use our 2 molecules of sulfuric acid. So I'll draw them in molecular formula. So this is our hydrogen, oxygen, then we have sulfur. Okay, this double bonds, oxygen, hydrogen. Yes. H2. Yes. Yes. And another mole of hydrogen, another molecule of hydrogen, sulfuric acid, sorry. We have to show them in a molecular formula to better understand the reaction at a molecular level. Okay, so a reaction will happen between these 2 molecules of sulfuric acid, where one oxygen, so preferably I'll choose this oxygen here, one oxygen will abstract a hydrogen from another mole of sulfuric acid. So you find that this oxygen here will use its lone pairs to abstract this hydrogen from this other atom, or yes, this other molecule, which is a sulfuric acid. So when the sulfuric acid has a reaction with this oxygen, we'll find that this oxygen will get a relatively positive charge based on the loss of these lone pairs, and we find that this molecule will now be present as oxygen with a positive charge, a hydrogen, and a hydrogen. So this intermediate won't last because oxygen is electronegative and it can't exist in this form. So oxygen would want to restore its natural electronegative form. So the only option oxygen has is to break its already existing bond between sulfur and use the 2 electrons to stabilize the positive charge. So this will result in the breaking of this bond, and from this breaking of this bond will produce H2O, which is water. We'll produce water here as a result, and we'll produce a sulfonium ion. Yes, a sulfonium ion as a result of that separation. So our sulfur here, okay, so this is our electrophile that we've created, which is a positively charged sulfur trioxide atom. Yes, sulfur trioxide atom, and this molecule is what we're going to use in the second step. So let's keep this, and let's keep the water as well, and let's keep our conjugate base. So as we react this hydrogen, we leave our oxygen unbonded. So this oxygen will remain relatively negative, giving us HSO4 negative, which is our conjugate base. So let's keep this one as well. So these three products have been realized from the first reaction, which is electrophile generation. An electrophile, water, and the conjugate base. Let's go to the second step of the reaction, where we look at attack, aromatic attack. So the newly formed SO3H electrophile, which has a relatively positive charge, is going to be reacted with our benzene ring, which is our aromatic compound in this case. So this relatively positive charge and this highly nucleophilic benzene ring will have an affinity. So one of these pi bonds is able to stabilize the positive charge on this electrophile. So this electrophile will be attracted to one of the pi bonds of the aromatic ring. So as a result of this union, you find that a pi bond, specifically in this case it's this bond here, it will break, so that a new bond will be formed between this SO3H molecule and the benzene. So we realize the following, where we have a bond that has been broken here and the SO3H molecule attached. So if this bond has been broken, this carbon and this carbon were involved in this bond. So this carbon is satisfied with this new molecule, but this carbon isn't satisfied with any new molecule. So there is a relatively positive charge on this carbon, and then the rest of the pi bonds maintain. Okay. So from this intermediate, we're able to realize resonance structures based on the movement of the positive charge between the ring or within the ring. So any adjacent pi bond to this positive charge is able to resonate to stabilize it, as we have shown there. So this bond will break in order to stabilize this positive charge, and we realize the following compounds or intermediates. Sorry. Okay. Follow through as we do the resonance structures. These could be important in other applications. So once this bond breaks, the other carbon that was involved in this pi bond, which is this carbon, will remain electron deficient. So a positive charge will be shown on this carbon, and a newly formed double bond between these two carbons, and these double bonds will maintain. Okay, so a double bond, there is a double bond adjacent to this positive charge. Apart from the newly formed double bond, there is an older double bond which can also stabilize this charge, and in doing so it will break this already existing pi bond to form a new pi bond. So that means there will be a positive charge on this carbon. So we have this structure. When this pi bond resonates, we form a new double bond here, and then this carbon that was involved will remain with a relatively positive charge. Okay, then the rest of the pi bonds maintain. Okay, so at this level, there is no other adjacent pi bond to this positive charge, unless the newly formed pi bond, and we can't break a newly formed bond. So that means we end our resonance structures. So after we have our resonance structures, we can now depict our uranium ion. And our uranium ion will be based on the migration of the charge, which is the positive charge, around the ring, and the limits the positive charge had reached. So let's try to trace the movement of the positive charge within the ring. So the positive charge had begun from here, it had resonated until there. So we'll start from here, this position. Okay, until there, yes. And then we indicate a positive charge to show resonance. So this is our uranium ion, and these are our resonance structures of this reaction. So let's look at the final step, which is restoration of aromaticity. Right, so as we are ending this reaction, we have to keep in mind of the products that were formed in the previous steps so that we utilize them in the following steps. So in this final step, which is step 3, we are restoring the aromaticity of the ring. So we use the first intermediate of the second step, which is the aromatic attack. So the first intermediate was as shown, where we had broken this pi bond that existed here, and we had a positive charge on this carbon here, and we had a pi bond here and a pi bond here. Okay, so this is what we use as our reactant in the third step. Yes, so we react this with our conjugate base, and as we recall, we had formed a sulfonium ion, which was negatively charged, HSO4, where we had removed one hydrogen to form water in the other sulfuric acid molecule. The remaining sulfuric acid molecule, which has lost a hydrogen, is our conjugate base, and we use it in restoring aromaticity. So pay attention to the carbon that has received the incoming molecule. So the carbon that has received the incoming molecule possesses a hydrogen, and so do the other hydrogens of this ring. So we use this hydrogen to restore the aromaticity, and react this sulfonium ion to this hydrogen to abstract this hydrogen and form a new bond, which will yield H2SO4, which is sulfuric acid, our catalyst. And after hydrogen reacts with the sulfonium ion, we realize that the bond between hydrogen and the carbon of the ring will be broken, and the electrons of this bond will be used to stabilize the positive charge in the ring. So from this bonding will result to a newly formed pi bond within the ring. Okay, so let me clean up just to depict what I've shown. Okay, so the first product will be our aromatic ring, which has a newly formed double bond, sulfuric acid, water as our final products.